What if I told you that there was a number that didn't actually exist, yet it was still a solution to this equation? Would you still have faith in me as your math teacher? Would you still listen to me for the second half of the year? Well, there is such a concept, and this equation serves as a great starting point to help you understand it. Let me show you. If we solve this equation, if we solve this equation, you would subtract 26 from both sides. And when you subtract 26, you would say that x squared now equals negative 36. As you continue to solve the equation, you would take the square root of both sides. Of course, when you take the square root of both sides, you would be taking the square root of a negative number. But let's just write it, let's record it as what it is, the square root of negative 36. And by the way, when you take the square root of both sides, you do get plus or minus. So let's put that in there. You always get a plus or minus from taking a square root. Well, you'll notice that I'm not trying to simplify this plus or minus square root of negative 36, but instead, I'd like to show you that this number, this x equals plus or minus square root of negative 36, it actually is a solution to this equation. How can that be? Well, it's actually pretty simple to see because all you got to do is plug it in. All you got to do is plug it in for x. And so we have this plus or minus square root of negative 36 squeezing itself in there for x. Now, of course, the first thing you're going to do, or as far as checking this answer, is you're going to square. And when you square, you're going to square away the plus and minus. Basically, no matter what you square, it always comes out positive. So we're kind of square away the plus or minus. But we're also going to square away the square root. Yeah, we're going to kind of cancel the square root. And that's going to leave you with what's under the square root. Now, what's under the square root is a negative 36. Is negative 36 plus 26 equal to negative 10? Well, by golly, it is. And what we see here is that we seem to have found a number which doesn't actually exist. That means that there really is no square root of a negative number. And yet, even though it doesn't exist, it still acts as a solution to this equation. Well, what we like to do with this number, the square root of negative 36, is we like to describe it a little bit more simply. And that is by describing it as an imaginary number. Now, yep, it is what I said. It's an imaginary number. And you see, it's imaginary because I can sort of split negative 36 to be thought of as negative 1 times 36, which then allows me to individually do the square root of each of these parts. And specifically, when I get to the square root of negative 1, which in its essence is the square root of a negative number, I can describe that with the letter I. The letter I being the representation of the square root of negative 1. Now, do you see here I can actually do the square root of 36? Yeah, I can actually do it. I can change it to the number 6. And so when we change the order of this, because it just kind of sounds a little bit better, when we change the order and write it as 6i, we are able to say that the square root of negative 36 is equal to this imaginary number known as 6i. Yeah, there's this thing called imaginary numbers. Imaginary numbers, also which will fit into the concept of complex numbers, isn't what maybe it sounds like. It doesn't mean that the problems are going to be really tricky or hard to understand. Instead, imaginary and complex numbers really just are referring to the square root of a negative number. And when you take the square root of a negative number, that is the square root of -1 in its essence, well, that is equal to I. That's equal to the symbol, or as we'll call it, the number I. So, can we sort of simplify a problem? Can we think about a problem with a now that we have this square root of -1 equaling I? Well, let's take a look. We most certainly can. Let's take a look at a couple examples of how we can work real simply with something like the square root of a negative number. So like the square root of -25. As you can see here, no longer are we going to say that this is just undefined. Instead, we're going to rethink of it as the square root of -1 times 25, specifically so that we can do the square root of -1 individually. And of course, the square root of -1 is defined as I. Now, the good news here is I can do the square root of 25 also. And of course, the square root of 25 has always been the number 5. When you rewrite this in the order that we like to see, we would call this 5I. Now, perhaps you'll be ready for a little shortcut. And as soon as you are ready, yes, what's really happening here is that the negative sign is basically coming out of the problem and turning into the letter I. When the negative sign comes out and turns into the letter I, it leaves behind just a good old positive number. And that positive number, we're able to simplify, we're able to perform the square root like we always would. Do you want to try a little shortcut with 3 times the square root of -16? I think we're ready to do that. The negative sign, it's really like a -1. And of course, when you have that under the square root, it comes out, it turns into the letter I. So now I have just the square root of a regular 16, which is really nice because that turns into the number 4. So when I do the square root of 16, I get the number 4, but that's still going to be multiplied by this 3i that's out front, which ultimately leaves me with 12i. Now 12i is an imaginary number, but it's a lot more proper, if you will, to describe using an imaginary number instead of having that strange negative under the square root. How about the opposite of the square root of -75? Now, the purpose of this problem is twofold. First off, there's nothing wrong with having a negative sign in front of a square root. We don't want to go bonkers and change everything into an imaginary number. But the negative sign that's under the square root, now, yeah, that's a problem. And that's going to come out, if you will, it's going to come out as an I. But as I hope you can see, I still have the negative sign in front of the entire answer. So now we're looking at -I square root of 75. Now the square root of 75 in itself is not a perfect square root. However, there is a number kind of inside of 75 that is perfect, and it's the number 25. Now when you rethink 75 as 25 times 3, that gives you the ability to do the square root of 25 separately from the square root of 3. Now, if you want to show that individual step, you'd be doing the square root of 25, like I said, separately with the square root of 3. Or perhaps you realize that the square root of 25 is also going to come out, and it turns into the number 5. Either way, we get a 5 on the outside, but we have the square root of 3 that still kind of remains on the inside. So when you write this final answer, we have the opposite of 5i root 3. And of course, that entire answer is imaginary, but That's better than having our answer written with a negative. You try. You try 7 times root negative 20. 7, the square root of negative 20. Now, are you bringing the negative out? Ultimately, that's like the square root of negative 1. As we've said a couple times, the square root of negative 1 turns into an I. Of course, that I is on the outside. I hope you can also see, the 20 is no longer negative. Now, the thing about 20 is that it has a perfect number. It's kind of built from a perfect number. Yeah, it's built from the number 4. Now, that specifically would be 4 times 5, but it's like we're thinking now about the square root of 4 separately with the square root of 5. And the good news is I can do the square root of 4. That turns into the number 2. But the square root of 5, I can't really do that. At least I can't do that evenly. So I now have 2 root 5. But that's being multiplied by 7i. Yep, the 7 and the 2 can multiply to be 14. There's still an I out here, and we end up with 14i root 5. Let's go a little deeper with the letter I. The letter I indeed is equal to the square root of negative 1. But what would happen if I square both sides? What would happen if I kind of change this so that now we're thinking about I squared? Well, I squared also has a value. And the cool thing here is if I square both sides, that's going to cause this square root to cancel out, leaving me with negative 1. Now, I'll tell you, kids, I squared equaling negative 1 is another key idea to take away from this imaginary lesson. But it doesn't stop there. I could actually multiply both sides by I, and when I multiply both sides by I get an I cubed statement. Now, I cubed would be I times negative 1, which comes out to be negative I. I cubed equaling negative I is another truth that we sort of use as we work through this chapter. And then there's one more that we can do. Now, that one more that we can do is to take my I squared. As I told you, that's a key idea. But I can actually square that. Now, if I square that, I'm going to end up with I to the 4th. I to the 4th, that's not a negative 4, that's just I to the 4th, is the same as negative 1 squared. Negative 1 squared comes out to be positive 1. So it's kind of interesting here. We see that if we start with the square root of negative 1 equaling I, we can actually create these other statements about I squared, I to the 3rd, and the I to the 4th. What can we do with this sort of interesting math? Well, we can do some simplifying. We can do some problems that will involve some sort of higher powers, like trying to simplify negative 3i squared. Negative 3i to the 12th. I misread my notes. Now, you might say, I to the 12th? Wait a minute, that's a really high power. Well, but the cool thing about I to the 12th is it can actually be thought of as some I to the 4th. You see, I to the 4th and another I to the 4th and another I to the 4th is going to give me a total of I to the 12th. Why would I think of this as I to the 4th? Well, remember what I to the 4th equals. It just equals the number 1. So the strange thing here is that this problem, negative 3 I to the 12th, is really just equal to negative 3. How about I to the 25th. Yeah, as you can see here, we're dealing with some like higher powers. Now, I to the 25th, that also can be thought of as some I to the 4th. If you need to see them all written out, we can do that. But do you realize how many I to the 4th I'm going to put here? What do you think? If you said I was going to reach a total of 24, you would be right. But there's still one more I that gets me to 25. You see, what's happening here is we're trying to find out how we can take a big power and basically think about it as the number 1. We can do that if we use I to the 4th. I ended up getting myself the whole way up to 24, but I still had one more I to get me to 25. So that's basically like 1 times I, which comes out to be I. How about a slightly smaller sort of I problem? Now, a problem like this, as stands, doesn't appear to have any higher powers, but if you apply what we were doing in the previous problems, you would realize that when you have a negative under a square root, that actually is going to pull out as the letter I. Well, there was already an I that was in this problem, and these two I's now come together to be an I squared. Now, the cool thing about getting I squared is that is on our list. That's on our list of powers. And oh, by the way, the square root of 9 you can now do, which comes out to be 3. Do you see where this is headed? I squared equals -1. And -1 times 3 is indeed -3. So it looks like I was able to ultimately convert this problem to equal a regular number. Yeah, the regular number, -3. Let's try one more. Actually, maybe it would be a good, you try. How about 5I to the 10th? Now, I to the 10th is clearly a larger exponent of I. As we did in the previous problems, if you can find I to the 4th that are inside of that 10, well, you'll be in business because I to the 4th is equal to 1. So if I have I to the 4th, but then still I squared, well, that's going to be the same as I to the 10th. What's going to happen with these I to the 4ths? Again, they equal 1. But what's going to happen with I squared? Well, you're going to learn that I squared is a pretty important value. It's equal to -1. Yeah, when you get I squared, it equals -1. So that means this whole problem is as good as 5 times -1, which of course is -5. Again, an actual, if you will, sort of real number, an actual kind of real number that came from 5I to the 10th. Here, why don't you try one more? If you haven't tried, or maybe you say, yeah, I haven't tried any, but try one. If you haven't yet, how about something like 7I to the 6? Maybe you're getting to the point that you can kind of just see that how this is going to work out. If you're saying, can I just write -7? You can. 100% you can do that. If you want to show the steps, you would break 6 into an I to the 4th, leaving you with an I squared. And again, I to the 4th is 1, but I'm telling you, I squared equaling -1. Now that's the key idea. Since I squared equals -1, then we have 7 times -1, which again is -7. There's one more sort of piece to this initial lesson. There's one more concept that we like to teach kids, and that is doing a little adding and subtracting of complex numbers. Now, the good news here, adding and subtracting of complex numbers actually just ends up becoming adding and subtracting what we call like terms. Let me show you. If we're going to do some adding and subtracting of complex numbers, such as like 2 plus 7i, and maybe like 3 minus 5i. Now, before we go any further, I do want you to realize that each of these groups is known as a complex number. What's a complex number? It's basically a number that's made up of a real number and an imaginary number. The real number is 2. The imaginary number is the 7i. Same thing over here. We have complex number. Okay, honestly, even though there's 2 numbers here, the whole group is known as a complex number because it has a real number and an imaginary number. Now, when you add and subtract complex numbers, it's just a matter of adding and subtracting like terms. So remember those real numbers? Yeah, they're like each other. If I add them, I get 5. Remember these imaginary numbers? Well, they're also like each other. If I add them, I get 2i. You just added those complex numbers. Yeah, it's actually pretty easy. It's something we like to kind of throw in on this first day because, as you'll find out tomorrow, we're going to do some multiplying and dividing. That's a whole nother animal, multiplying and dividing. But hey, right now we're just adding and subtracting. So what do you think? It's a subtraction problem, right? Remember, whenever you're subtracting, you have to, if you will, distribute that subtraction sign into the parentheses. I always like to say that you're going to change it to a plus sign, but then you're going to basically switch the sign on each value in the parentheses. So now we're back to basically adding like terms. Yep, if you add those up, you get -1. And if you add the imaginary numbers, -3i and +2i, you actually get -1i, which if we're going to write that kind of a little bit more simplified, it's just nothing more than -1 minus I. Okay, now, imaginary numbers. What we got to do is we got to kind of get past the point of, of maybe being grumpy about this whole idea about a number that doesn't exist, and realize that it's part of algebra. There will be uses for this, I promise. But right now we're just trying to get a little comfortable. Trying to get a little comfortable with the main ideas. That is essentially the idea that the square root of -1 is equal to I. And then we even get into some powers that kind of are equivalent to other values, which we'll start to use in these simplifying problems. The homework sheet, what you're going to do is you're going to complete parts A, B, and C. So again, on the homework sheet, you're going to do parts A, B, and C, and then we'll pick up the lesson with multiplying and dividing tomorrow.